This lesson is on basic types of parent functions. We're going to be looking at some of the basic parent functions that you already know and you've seen before, as well as some transformations of those functions. We're going to do the first page together, as well as all of the parent functions, and then you're going to be left to do the others on your own. So our first equation is f of x equals x, and you should recognize this as a line or a linear function. And it's actually the linear parent function because there are no transformations for this function. So we're just going to draw our line straight through the origin. For each of these, we're going to be graphing them on our own, but if you wanted to, you could always check in your calculator. So you could go to your calculator, go to y equals, type in x, take a look at your graph, and you should notice that it matches exactly what we sketched out. So we did the sketch of the graph. Now we're going to talk about domain and range. Remembering that domain is our x value, so we are looking how far left and how far right the graph goes, and range is our y values, so we are looking how far down it goes and how far up our graph goes. So let's take a look at this function. If you notice, our sketch has arrows going in both directions, meaning that it extends to infinity. So for the line f of x equals x, both our domain and our range are going to be all real numbers, written in interval notation exactly as you see it. Next, we want to look at any symmetry that this graph has. So if we take a look at this, there is no symmetry on the x-axis or the y-axis, but it does have symmetry about the origin, meaning that if I take this point over here, which is 2, 2, and I reflect it through the origin, if you remember from geometry, the point over here, negative 2, 2, is also on the graph. So this has symmetry about the origin. And if you notice, some of our columns are going to have real life scenarios that model the function. Not all of them will. We picked out some that are important for you to know for some of the key parent functions. So for a linear function, an example would be the cost of a gym membership is modeled by C of t that charges a flat amount for the initial sign up plus $20 per month. Now the reason this is a linear model is because it would be a constant rate of change. That membership that you're paying per month is changing by the same amount every month. You're adding $20 each month. So our next function, f of x equals 3x, is also a linear function, but this time there's some transformations happening. But this is still a linear function. Now, if you notice, the difference is that there's a 3 in front of the x. And if you remember from transformations, a 3 in front means that it's being scaled vertically, which means it's being either stretched or shrunk vertically. So it's going to be getting taller or shorter. And because it's a 3, it's larger than 1, it's going to stretch. So we're still going to have a straight line, but it's going to be a little bit steeper. And once again, we're doing this based on our knowledge of transformations, but you can always check in your calculator. So if we go to our calculator, we go to y equals, clear out what you have there. I'm going to type in 3x, go back to my graph, and there we go. It's a line, but it is a steeper looking line. So domain and range, there are still arrows on the end that are pointing in opposite directions, which means that once again, my domain and my range are all real numbers. And now let's talk about our symmetry and transformations. Well, we talked about the transformation already. It's a vertical stretch by a factor of 3. And let's look at our symmetry once again. This one is also symmetrical about the origin. All right, so those are our two linear functions. Now let's move on to our next function. Our next function is f of x equals x squared. You should recognize this as a quadratic function, and it is the parent function for the quadratic family. And we know the shape of that. It's going to form a parabola, and our basic parent function for the quadratic family looks like this. It has the points 0, 0, 1, 1, and negative 1, 1. Those are three key points you want to take notice of, because when there are transformations occurring, you're going to take those 3 points and move them up, down, left, right, or so on. So let's take a look at our domain for this function. We have arrows pointing in both directions, but they are both facing up. So domain is x. How far left does it go, and how far right does it go? Those arrows are pointing on the left towards negative infinity, and on the right towards positive infinity. So our domain is all real numbers. For range, we are talking about bottom to top. So how far down does it go, and how far up does it go? Well, this graph starts at 0, and 0 is included in the graph, so it gets a bracket for interval notation. And both of our arrows are pointing up, so it goes up to positive infinity, and it will never come back down because both of those arrows are pointing up. So let's take a look at our symmetry and transformations. Well, this is our parent function, so there are no transformations occurring. And symmetry, if you take a look at this graph, it's symmetrical over the y-axis. If I took my paper and I folded it in half on the y-axis, the left side and the right side would match up. So this is symmetrical over the y-axis. And as I said, some of these parent functions will have scenarios to go along with them. The quadratic function does. It says the height of a ball t seconds after it's thrown into the air from the top of a building can be modeled by h of t, where h of t is height in feet. All right, so let's take a look at our next quadratic function. You'll notice it's quadratic because it is an x squared. F of x equals x squared plus 2. So we still have a quadratic function, but this time there's a plus 2. So I'm going to go right to the transformations column. If you notice that plus 2 and you remember from transformations, it is on the outside, so it is a vertical shift up 2 units. So what we're going to do is we're going to sketch our function, keeping that parent function in mind from before that we graphed, except everything is going to be moved up 2 units. So there is a picture or a sketch of our parabola. Once again, you can always check this on your calculator. So if I go to my calculator, go to the y equals, clear out what we have there, x squared plus 2, take a look at your graph, and it should match exactly what we just sketched. So let's talk about domain and range. Once again, our domain of this function, how far left and how far right, is going to be negative infinity to positive infinity, all real numbers. And our range, bottom to top, it goes as low as 2. And then those arrows are pointing towards infinity, so it's going to go to infinity. Now, if you notice in comparison to the parent function, Our original parent function, f of x equals x squared, the range was 0 to infinity. For this function, it had a vertical shift up 2, so our range changes. Instead of being 0 to infinity, it moved up 2, so it is 2 to infinity. And we talked about transformations, but you should notice symmetry as well in this graph. Just like the parent function, it is symmetrical about the y-axis. All right, so let's turn it over and take a look at our next function. So we have f of x equals the square root of x, and this is our square root function. Because there are no transformations happening, this is our parent function for the square root. And our square root function looks like this. Some key points to talk about here: 0, 0, 1, 1, and 4, 2. There are others, but those are some key points that you can keep in mind when we are talking about transformations. So, domain and range. Domain, how far left and how far right. Well, our graph to the left starts at 0. And once again, it's included, so it gets a bracket. And that arrow is pointing to the right, which goes to positive infinity. So our domain is 0 to infinity. Our range, bottom to top, it starts at 0 for the y values as well. And that arrow is pointing towards positive infinity for y as well. Symmetry and transformations. Well, this is our parent function, so there are no transformations. And if you take a look, there's no symmetry for this graph. It does not have symmetry on the x-axis, the y-axis, or the origin. So there is no symmetry. Just of note, it is only in the first quadrant because we're talking about the square root. You can't take the square root of a negative, and your square root will never give you a negative number. So that's why it's only in the first quadrant. The next function on your worksheet is f of x equals the square root of x minus 1. That one we're going to leave for you to do on your own. We're going to continue going through all of our parent functions. So our next function that we're going to look at together is f of x equals the absolute value of x. So this is our absolute value function. And once again, it's our parent function because there are no transformations occurring. If you remember, absolute value forms the V shape on our graph. It passes through the points 0, 0, 1, 1, and negative 1, 1. Let's take a look at our calculator quickly to remind ourselves of where we can find the absolute value bars if we do want a graph. So if I go to y equals and I clear out whatever I have there, if you hit the math button, located right under the green alpha button, then you go to the right, you will see ABS, hit enter, that stands for absolute value. Type in, for us, it's going to be an x, and take a look at your graph. It looks exactly like what we predicted. So let's go back to our worksheet and let's talk about domain and range. Domain, left and right, there are arrows pointed towards the left side and towards the right side. So once again, we have all real numbers, or negative infinity to positive infinity. For range, it starts at 0 and it is included, so I have my bracket for interval notation. And those arrows are pointing upwards towards positive infinity. So let's talk about symmetry and transformations. There are no transformations because this is our parent function, but you should notice this graph does have some symmetry. Just like the parabola or our quadratic function, it is symmetrical over the y-axis. Remembering that that means if I take my paper and I fold it in half along the y-axis, the two pictures will match up. And just of note, the reason this graph is only in the first quadrant and the second quadrant is because our absolute value is always positive. So the next function there is f of x equals negative absolute value of x, which we're going to leave you to do on your own. So if you could turn to the next page and move on with me to our next parent function. At the top of this page, we have f of x equals x cubed. So this is our cubic function. And this is the parent function because there are no transformations happening. And our cubic function looks like this. And the three key points we want to talk about is 0, 0, 1, 1, and negative 1, negative 1. This may be a function that you're not as familiar with, so don't forget you can always check it in your calculator. Domain and range. Domain for this function, left to right. There are arrows pointing in both directions towards the left side, which is negative infinity, and towards the right side, which is positive infinity. For range, bottom to top, same thing. We have arrows pointing in both directions, so it is all real numbers. For symmetry and transformations, there are no transformations because this is our parent function. But if you take a look at it, you should notice that this has symmetry. And it is similar to our linear function because it has symmetry about the origin. And the cubic function, we do have a real-life scenario for you. It says a box can be created by cutting out squares from the corners of a rectangular piece of paper. The volume of a box can be modeled by the function v of t. The next function we're going to leave you to do on your own because it's a transformation of the cubic function. So let's move down to f of x equals 10 to the x power. Notice that the variable is in the exponent, so this is our exponential function. So our exponential function is going to look like this. Remember that it's always passing through the point 0, 1 when there are no transformations. And this function actually should be a little bit steeper, so let's fix that because it's 10 to the x, so it has to pass through the point, we said 0, 1, but it also has to pass through the point 1, 10 because it has a base of 10. As your base changes, that point will change as well. So for example, if we had f of x equals 2 to the x, that point would be 1, 2. Or if we had f of x equals 6 to the x, it would be the point 1, 6. Okay, so let's take a look at our domain for this function. Domain, we are talking left to right as always, and our arrows are pointing to the left towards negative infinity, and to the right towards positive infinity. For the range, if you remember when we first talked about this function, we said that there was an asymptote. So let's dash in that asymptote. Our asymptote is the x-axis, which means our graph will approach it, but it will never touch it. So our graph approaches 0, but it does not touch it, so it gets a parentheses for interval notation. And that arrow is facing up towards positive infinity for y. So our range is 0 to infinity. Let's talk about some symmetry and transformations. There is no symmetry for this graph. And there are no transformations. So we do have some room here. Let's just make ourselves a couple of notes. It passes through the point 0, 1. So our parent function will always pass through 0, 1. If there are transformations, that point will move along with those transformations. And we had an asymptote on the x-axis. So although it's not transformations or symmetry, they are some key things you want to remember about the exponential function. And once again, there's a real-life scenario modeled by exponential functions. The population of a town doubles every 10 years. So anytime it's changing by a constant factor, it doubles, it triples, it quadruples, it halves, it quarters. All of those are going to be exponential functions. So at the bottom of this page, you have another function, f of x equals 10 to the x plus 3 minus 2. We're going to leave you to do that one on your own. So flip it over and let's take a look at our next parent function. So we have f of x equals log x. So as you can guess, this is our logarithmic function. Which of course is the inverse of the exponential function that we just did. And remember, this is a common log. There is no base given, so this is the same thing as f of x equals log base 10 of x. Because remember, anytime there is no base, we understand it to be 10. And you should remember from when we did those graphs, it's going to look like this. It's going to pass through that point 1, 0. So whenever we have a parent function of a log, it is always going to pass through the point 1, 0. And then from there, any transformations, that point will move as well. And another key point, if you want to mark it on your graph, would be the point 10, 1. And that, of course, is because we have a base 10. If we had log base 2, that point would be 2, 1. If we had log base 7, that point would be 7, 1. So domain and range. How far left and right for the domain? Well, once again, we have an asymptote for this graph. So let's sketch in that asymptote. This time it is on our y-axis. So for the domain, that graph will approach 0, but it will never touch it or cross it. And then that arrow is pointing towards positive infinity. So our domain is 0 to infinity. For range, that arrow is pointing down and up. So our range is all real numbers, which is negative infinity to positive infinity. Symmetry and transformations. Once again, there are no transformations because this is one of our parent functions, and there is no symmetry. So just like with exponential, because we have some room here, we're going to take some notes on some key things you should know about the log function. Remember that it passes through the point 1, 0. And once again, if there are transformations, that point will move. And then we had an asymptote on the y-axis this time. And that will move as well with any transformations that occur. The next function is f of x equals log of x minus 3 plus 4. We're going to leave that one for you to do on your own. So we're going to move on to our next parent function, which is f of x equals sine of x. So if you remember back to trig, we're going to be graphing sine. Just as all of them have names, sine of x has a name as a parent function. It is called the sinusoidal function. So that may not be something that you're familiar with, but it's another name, and it kind of looks sinusoidal, looks like sine, so that's how you know. So if you remember back to trig, sine always starts at the midline, then it goes to the maximum, to the midline, down to the minimum, and back to the midline. And then in the opposite direction, going to the negative x values, it goes to the minimum, midline, maximum, and midline. So this is our sine function, remembering that it goes as high as 1 and as low as -1. Now we haven't talked about how to graph this on your calculator, but we do want to show you in case you want to check it on your calculator. So if you go to y equals, you clear out whatever is there. You're going to type in sine x. And then we're going to go to zoom, and you're going to choose choice 7, which says zoom trig. So you can either hit the 7 or scroll down and then hit enter. And this is the picture of your sine function. So if you do want to check it on your calculator, that way you know how. But you should remember these from trig. So our domain, remember that there are really arrows on the ends of this graph. So it is going negative infinity to positive infinity. It's a periodic function that just keeps repeating over and over and over again. And for our range, remember that it will only go as low as -1 and as high as +1. So our range is -1 to 1 with brackets. This is our parent function, so there are no transformations, but it does have symmetry. If you take a look at this, it is symmetrical about the origin. And once again, this has a real-life scenario for this parent function. A homeowner notices that her heating bill is the lowest in the month of August and increases until it reaches its highest amount in the month of February. After February, the amount of the heating bill slowly drops back to the level it was in August when it begins to increase again. So that story, it goes up and down and up and down, just like our sine function, which goes to its maximum, back down to its minimum, and so forth. It's a periodic function. So next is f of x equals negative sine of x plus 1, which is for you to do on your own. So flip it over and let's take a look at our last two. This parent function, f of x equals the cube root of x. So this is our cube root function. And our cube root function is going to look like this. Our key points are 0, 0, 1, 1, and -1, -1. Not a function you may be too familiar with, so if you want to check it on your calculator, if we go to y equals, clear out what you have there. To get that cube root symbol, you're going to hit math and choose choice 4. And then you see your cube root symbol appear. We're going to type in an x. And our graph, if you go to your graph right now as it is, it's still zoomed in to trig. So to get out of that, you're going to hit zoom 6, which will bring you back to the standard window that you're used to seeing. So there's our standard window, and our picture should look just like we predicted. So back to our worksheet for domain and range. Our arrows are pointing left and right, so our domain is negative infinity to positive infinity, and the same thing with our range. Both the domain and range are all real numbers. This is our parent function, so we have no transformations, but it does have symmetry. This is symmetrical about the origin, just like its inverse, x cubed, and just like the linear function. The next function, f of x equals 2 cubed root of x, is a transformation, so that's for you to do on your own. And then we're going to move down to our very last function, f of x equals 1 over x. Now, this is not a function that you've seen, but it could come up, so I do want to show it to you just in case. This is our rational function, and it is the parent function. Sometimes you'll see it known as the reciprocal function, but we call it a rational function. And our graph is going to look like this and like this. Key points, -1, -1, and 1, 1. There are two asymptotes in this function. This graph will never touch the x-axis or the y-axis, so I'm going to sketch in both of those asymptotes. So for our domain, it's everything except 0. All real numbers except 0. And it's the same thing for the range. All real numbers except 0. But I want to show you what that looks like in interval notation. It would be -infinity to 0 with a parentheses because it does not touch it, and then a union 0 to infinity because it does not touch 0, but it includes everything else. So 0.000001, everything else nice and close to 0. So this is the same thing for the range, all real numbers. Okay. And then it is symmetrical about the origin, so let's write that down in our symmetry and transformations. And then we just want to make ourselves a note. It has asymptotes for x-axis and y-axis. So this is a function that does not come up that often, but I did want to show it to you just in case, so you have that. And then your last one is a transformation of the rational function. F of x equals 1 over x minus 3 plus 2. So that's for you to do on your own. So we have gone through all of our parent functions. You have seen the linear function, the quadratic function, the square root function, the absolute value function, the cubic function, the exponential function, the logarithmic function, the sinusoidal function, the cube root function, and the rational function. So now you're going to take some time, go back through the ones that we did not finish, and do the same thing. Use your knowledge of transformations to move those key points I gave you. Look at the domain and the range. If you need to check it with your calculator, of course, go ahead and do that. Then identify any transformations and any symmetries that you have.